Hello, my name is Iago Silvestre, and I would like to briefly present the paper that me and Professor Leandro Becker submitted to the work in progress track of SBESC named Performance Analysis of Embedded Control Algorithms Using UAVs. So the main objectives of this paper was to test the control programs used in our project and see if they could be executed within the deadlines, and to help detect where are the bottlenecks in the control algorithm implementation. This would allow us to iterate and explore modifications in software and hardware to meet the deadlines and assure the system stability. For this paper, we used the Gem5 simulation tool, which offers various CPU and memory models, and also supports a high variety of instruction set architectures, such as ARM, RISC-V, and x86, among others. The system test consisted of basically two control strategies, which use LKR, and the other one used a mix of H2 and H infinity, and they were both designed with a control window of 12 milliseconds. They also were compiled with floating point operations being solved by software. They varied, however, on the feed-forward implementation, where the LKR dealt as a constant disturbance, which could be solved by a simple addition on the control variable, and H2 H infinity used a set of matrix operations to determine this disturbance. Inside the simulation, we also configured the hardware to be similar of a Raspberry Pi 3B Plus. We chose this hardware configuration in order to compare the obtained results of the simulation with tests that we could execute with the real hardware. So here we have the initial results of the LKR control program. We can see that in average it took 50 microseconds to execute the control program, which is well inside the 12 milliseconds control window, and that it had an average of 10.3% of CPU idle cycles, which is relatively low. Here we have the first results for the H2 and H infinity control program, and we can see that these are very different results from the LKR, which this program took an average of 34 milliseconds to execute, which is well above the 12 milliseconds control window. We can also see that the idle cycles of this control program were very high, of around 45%. And we can also see that the RAM was very utilized on this control program, with an average of 12.2 megabytes being read every control loop, and that it also showed us a relatively high memory bus utilization of an average of 9%. So with these disturbing results of the H2 H infinity, we went ahead and we tested the same control program on the Raspberry Pi 3B Plus development board to verify the simulation data. After this first control loop, the average mismatch was of around 20%. And we can see that even in the real tests, the execution time was well above the 12 milliseconds control window. So as mentioned before, the H2 H infinity varied from the LKR implementation on some aspects, and one of them was the feed-forward implementation. We went ahead and we only tested on the Gem5 the feed-forward function, and we saw that from the 33.4 average execution time, 33.3 was being used on the feed-forward function, which evidenced that this was the bottleneck of the control implementation. As mentioned, we would like to test the capabilities of Gem5. So we made a test where the level 1 and level 2 caches of the CPU were increased to 128 megabytes each, which is a very unrealistic test since most modern CPUs have level 1 and level 2 caches in the kilobyte scales. But this test was intended to isolate the CPU operation and avoid any idle cycles generated through RAM interactions. The results shows us a 52% drop in execution time, and as expected, the CPU idle cycles dropped from 45% to around 2%. We also would like to test an improvement in the CPU architecture, so we went ahead and we tested a change of architecture from the Raspberry Pi 3 to the architecture using the Raspberry Pi 4, which is the Cortex A72. So we can see in the image the comparison between these two types of architectures, and we made two sets of tests. The first one consisted of the same cache values which we had on the Raspberry 3B Plus, and the second set of tests we maximized the amount of cache available in this architecture. So here we see the results of this modification, and we see that we had an average execution time improvement of around 32%. And the first test was 33, and in the second test was 35. And we also had a considerate decrease of CPU idle cycles, where in the first test we had an improvement of around 21%, and in the second test it improved 24%. So we concluded that Gem5 was a valuable asset to test and determine this control program characteristics. We saw that the LKR program showed good performance in all the tests that we made, and that the reason the mix of H2 H infinity was not able to meet the 12 milliseconds control window was because of its feed-forward implementation. We also realized how a change in CPU architecture can improve the control execution time. So for future works, we would like to evaluate the impact of changing the instruction set architecture. We would like to test other control methods that are used in the Provant project, such as model predictive control. We would like to explore the use of customized operating systems to reduce the amount of background processes, and evaluate the use of floating point hardware compile and how this would impact the control performance.